Okay. So in my notes I've written here CLT. What does that stand for? Central limit theorem. So that's what we do today. This is while it's very old, people today mathematicians today are still proving central limit theorems in various contexts. Even me. I wrote a paper recently on the subject. I guess the word central should give you an idea that this is pretty important. The classical central limit theorem was proven for binomial random variables. We did it when p is a half, but we can do it a little more generally than that. So let's take let x1 through xn be IID random variables. And maybe, let's say the list goes on and on and on. Let's see, where's the, there it is. Let's say they have mu as their mean and sigma squared as their variance. So I said the mean of x1 is mu and the variance of x1 is sigma squared. What about the mean and variance of x2? Because, right, they have the same distribution and the distribution determines the mean and variance, right? Then, if we have that, we add up the first n random variables. And we look at the probability that this expression is less than or equal to x. What's the mean of Sn? What's the expected value of Sn? Pardon? N mu. What's the expected value of a sum of random variables? It's the sum of the expected values, right? So if we add up the expected values of these guys, all of them are mu, and there are n terms, so it'd be n mu. So n mu is the mean of, or the expected value of Sn. What's the variance of Sn? Well, what's the variance of a sum of independent random variables? Do you remember this? It's the sum of the variances. And each one has variance sigma squared, so the variance of Sn would be n times sigma squared. So this is the square root of the variance. So what would the expected value of this random variable be? What's the expected value of that? Well, I've subtracted the expected value from Sn. If you subtract the mean from a random variable and then take the expected value, what do you get? You get 0. So expected value of this is 0. What's the variance of this? 1. What's the variance of a times y if a is a constant?
A squared or y.
Right, it's a squared y. I'm sorry, a squared covariance of y. Right? So the variance of this would be 1 over sigma squared n times the variance of the numerator. What's the variance of the numerator? Sigma squared n. So the variance of this thing is 1. So this random variable has mean 0 and variance 1. And the remarkable thing is that as long as this and this happen, and they're independent and identically distributed, it doesn't matter what the distribution is, this will converge to that. So I see somebody's puzzled about this.
Is that supposed to be for variance?
Oh, I see why you're puzzled. Okay, thanks. Okay, this is the distribution function for the normal random variable with mean 0 and variance 1. So in other words, this guy asymptotically has a normal distribution with mean 0 and variance 1. Okay. Well, let's try to see why this is true. I would say let's prove this, but then you might panic or get scared or think you can't understand it. It's not that difficult. It's just calculus. Let's compute the moment generating function. And see what happens to that. Okay. Do we know what the moment generating function is for the normal with mean 0 and variance 1? It's e to the t squared over 2. Let's see if this converges to e to the t squared over 2. All right. I think this is legitimate. Here I can think of having Sn over this number and then minus n mu over this number, right? And then so that means I have e to a difference. And if I have e to the a minus b, that's e to the a times e to the minus b, correct? Where b is this part and this is the a. But now I'm taking expected values of this, and this one is random, but this one is not. So I can pull the non-random one out of the expectation. And then Sn is the sum of the x's. And again, I use the property of exponentials. E to a sum is the product of the e to the individual thing, sum ends. Okay. And now, let's use the fact that these are independent. So all these random variables, e to these things, are going to be independent. And the expected value of products of independent random variables becomes the product of the expected values. So I get expected value of e to the t over sigma root n times x1 And I'd get the same thing with an x2 and an x3 and an xn. And all of those factors would be identical because they're identically distributed. So I multiply this thing times itself n times, so I just raise this to the power n. Okay. And now I'm going to put this back inside. It's something raised to the nth power. What is it? It's this thing raised to the nth power, right? So when I put it back inside, here's an nth power here. I just put this inside. Okay? So far, so good. Okay. Now, what is e to something? Okay. It's that. And when x is very small, e to the x is approximately 1 plus x squared over 2. Because what happens to powers of really small numbers? They get even smaller, right? Like 10 to the minus 3, if you cube that, that's 10 to the minus 9, which is a lot smaller than 10 to the minus 6, I guess, right? So in other words, you can ignore terms past this when x is really small. Okay, so let's do that. In here, what do we get? We'd get expected value of, well, when k is 0, well, we get expected value of this thing where we substitute this in for little x, right? So we'd have a 1. We'd have a t over sigma root n times x1 minus mu. And then plus a t squared over 2 sigma squared n x1 minus mu squared raised to the n. So this is about equal. And the limit as n goes to infinity, we get the same thing, both here and here. Okay. Now let's take the expected value of this expression. Expected value of 1, well, I expect 1 to be 1. Expected value of this, well, here's a random variable from which I've subtracted its expected value. So the expected value of this difference would be 0. So this goes away. And the expected value of x1 minus mu squared, that's the variance of x1. And here's the variance of x1 down here. So when I take expected value of this, it cancels with the sigma squared in the denominator, leaving t squared over 2n. And all this is raised to the power n. Okay, so in the limit, these two are the same. What does this do as n goes to infinity? That's one of the fundamental limits from calculus. you remember how to do that? Good.
Use a logarithm.
You take the log. So let's take the log of this. Okay, so if we write s equal 1 over n, this is a log of 1 plus s times x over s. And taking the limit n goes to infinity corresponds to taking the limit s goes to 0. Right? What's the limit of this as s goes to 0? What happens in the numerator? It goes to log of 1 or 0. The denominator goes to 0. So this is called the indeterminate form. So the limit of this is the same as the limit of the ratio of the derivatives. What's that called? So you speak French. That's good. L'hôpital. So as s goes to 0, this is the same as the derivative of this with respect to s, which is what? X over 1 plus sx. How do you differentiate the logarithm? You get 1 over the thing inside times the derivative of the thing inside. And the derivative of this with respect to s is 1. And as s goes to 0, this goes to x. Right? That stays x. This goes to 1. That's 1. So x divided by 1 is x. So the log of that thing goes to x, so that thing must go to e to the x. Okay. So always remember this limit. So what happens here? This goes to e to the t squared over 2. X is t squared over 2 here. And that's the moment generating function for normal. With mean 0 and variance 1. Okay, so we proved that the moment generating function for this thing converges to a normal. So we need something that tells us if that happens, then the distribution functions converge. This is a distribution function for that random variable. It's converging to another distribution. Or the moment generating function for this is converging to the moment generating function for that. What about the distribution functions? Well, there's a theorem that says that. And that's called the continuity theorem. So let me write that down. So you have a sequence of random variables. Our Zn would be this guy. And Z is another random variable. And the moment generating functions for the Zn's converge to the moment generating function for Z for all t in some interval containing the origin. then limit n goes to infinity, the distribution function for Zn at z is equal to the distribution function for capital Z at little z at all points of continuity of the function f sub capital Z. So in particular, if capital F sub Z is continuous everywhere, then this convergence would take place everywhere. So that covers our situation. Here's our Zn. Moment generating function converged in an interval containing the origin to the moment generating function for the normal. So it says that the distribution functions for Zn converge to the distribution function for Z. So that's the central limit there. Okay? So what does this apply to? If these are independent Bernoulli random variables with probability P of success, then this random variable is approximately normal with mean zero and variance 1 distributed. So I'm saying that NP, or P, is the expected value of x1, and that P times 1 minus P is the variance of x1, which is what we've already computed before. Remember, for Bernoulli's, probably x1 is 1 minus probability that x1 is 0 is P. So the expected value of x1 is P. The variance of x1 is expected value x1 squared minus the square of the expected value. But x1 squared and x1 are the same, because if I square 1 or 0, I get 1 or 0. So this is the same as the expected value of x1. So this is P. This is P squared. So I get P minus P squared. That's P times 1 minus P. So here I've divided by root n times the variance. So that's approximately normal. So if n is 20 and p is 1/4, approximate the probability that Sn is bigger than 3/8. Sn is bigger than 3/8 n, say. Let's approximate that probability. Sn is the number of successes in n equal to 20 trials. About how many successes would you expect in 20 trials if the probability of success is a fourth? About 5, right? This number would be what? 3/8 times 20 is a bit more than 5. How much more, though?
Like 7.
Yeah, 7.5 or so. So we're asking what's the probability we have maybe 8 or more successes. So how would we do this? Well, we can actually compute this exactly because we know that the sum of n independent Bernoulli random variables is binomial. So this could be computed explicitly. It's the sum k equal, well, let's see, to be precise, 3/8 times 20 plus 1. I take the greatest integer in 3/8 times 20, and I add up to 20. And I have 20, choose k, 1/4 to the k, and then 3/4 to the 20 minus k. And all you have to do is compute all these numbers and add them up. And 3/8 times 20 is what exactly is that? 3/8 of 20 is 3/2 times 5. Half of 5 is 2.5. 2.5 times 3 is 7.5. So the greatest integer in that is 7. So here we have 8 to 20. That's 13 terms. And so we have to compute these 13 numbers and add them together. Now that's not impossible. Can you do it before the break, do you think? We have 12 minutes till break time. Maybe if you had a calculator. If you don't have a calculator, no. Okay? But the central limit theorem says we don't have to compute this. It says we should approximate this by a normal instead. So how do we get this into a form where we can use the central limit theorem? Well, what expression occurs in the central limit theorem? We have to subtract, if we have a sum, we have to subtract n times the mean and divide by root the square root of the variance times the square root of n. Okay? So in here, if we want to compute this probability, we should subtract np and divide by root n p 1 minus p. And in order to keep things honest, we should do the same thing here. We take 3/8 n, subtract p times n, and divide by square root of n times p times 1 minus p. That's the probability we want now. Okay, so let's, we don't need to figure out what this is, but we do need to figure out what this is. This is the random variable that's approximately normal, so we don't have to do any computation there. Here's where the computation has to be done. We have to insert n equal 20 and p equal a fourth. Okay, so let's do that. So, but maybe I'll just okay, so I'll factor out the 20. What's 3/8 minus 1/4? 1/8 of 20 is 1/4 of 20 is 5, so 2.5, right? Okay, so the numerator is 2.5. N is 20. 3/8 minus 1/4 is 1/8. 1/8 times 20 is 2.5. And down here, what do we get? 20 times a fourth times 3/4. What's 20 times a fourth? It's 5. 5 times 3/4, 15 fourths. Okay. let's simplify this a little bit. We can pull out the 4 from here. It becomes 1/2 in the denominator. And what does that become then? 20 over square root of 15? Is that right? I have a 10 here, and I have a 1/2 in the denominator. If I invert and multiply, I get 2 times 10 is 20, and square root of 15. And what's 20 divided by square root of 15? Certainly somebody must have a nice calculator here today. Any volunteers to compute that? This star means this thing here.
5.16.
Okay, so how do we find that?
Professor,
Yeah.
you have 2.5 divided by 1/2. Shouldn't that be 5?
Oh, this is, I thought this is 2 times 5. Oh, I can't read my own writing. Thank you. Okay, so this should be 10 then instead. 5.
2.5.
But, all right, 5. All right. Oh, yeah. Okay, 5. So now, and that was 1/4 of what we had. So 1/4 of this is 1.39. Okay. 1.29? Okay. 1.29. So how do we find that?
Now use the table.
Now we use the table. Okay. And so I'll do that. Table 2. And we want 1.29. And I look down the left column for 1.2 and then way over until I get to the column under 0.09. And this probably is 0.9015. Okay. And that is I think that, is that right? Okay, which is a lot faster than doing this computation. Okay. Now the central limit theorem appears in other forms. Another form of normal approximation occurs for Poisson random variables with large lambda. Okay, so let x be Poisson with parameter lambda. Then the expected value of x is lambda, and the variance of x is also lambda. Remember the moment generating function for Poisson? Is that, and that allows you to compute the mean and variance quite easily. If I take the log of this, the derivative of the log of the moment generating function evaluated at 0 is the expected value of the random variable. If I take the derivative of this with respect to t, yeah, this stays there, and I differentiate this, getting e to the t, so I get lambda e to the t as derivative. Evaluating at t equals 0 gives me lambda. And the second derivative at t equals 0 gives a variance, always. Doesn't have to be Poisson for this to be true. But now if we differentiate this twice, what do we get? First time we get lambda e to the t. If we differentiate that again, you get lambda e to the t. Evaluating at t equals 0, you get lambda. Okay? So, pardon?
I thought the second derivative would give you the expectation of x squared.
That's of m itself.
Oh.
But not when you take log.
Okay.
Yeah. That's one nice thing about the log, then you get the,
Oh, cool.
yeah. Yeah, if you take the second derivative of m at m directly, you get the expected value of, at 0, you get the expected value of x1 squared. Yeah. Okay. So, this random variable has what expected value? X is Poisson with parameter lambda. We've subtracted the,
Value is 0.
yeah, the mean, so the expected value of this thing would be 0. Why doesn't the root lambda affect that? Well, it's a constant. I could pull out 1 over root lambda from the expectation, and then I have the expected value of this minus that, which would be 0. What about the variance of this random variable? It's, well, it's lambda. But if I divide by this, then it becomes 1. So this random variable has mean 0, variance 1. Not everything that has mean 0 and variance 1 is going to be normal or close to normal. But let's compute the moment generating function. And if we get e to the t squared over 2 as a limit as lambda goes to 0, what can we conclude about x minus lambda over root lambda? It's nearly normal if lambda is big. Okay. So I'll do the same thing again. I'll pull out the deterministic part, or in other words, the non-random part. Okay. And now, I know what this is. I wrote it down up there. But we're evaluating not at t, but at t over root lambda. I know it looks a little perverse to write lambda over root lambda, but let's keep it for now. Maybe it'll be useful in that form. And then we have, this becomes e to the lambda, e to the t over root lambda minus 1. Okay? And now lambda is going to be really big. So what about t over root lambda? It's going to be really small. So here we have e to a really small number. And when we have e to a really small number, what approximation could we use? Oh yeah, over 2. Thanks. Okay. So actually, maybe now I'll change this to the first term to e to the t times root lambda. And I have e to the lambda times, I'm going to use the approximation that this is going to be like 1 plus t over root lambda, and then t squared over 2 lambda, right? And minus 1. What happens with this minus 1 when I put that in? This 1 and this cancel, leaving just the linear term and the quadratic term. So that means I have a lambda and then t over root lambda, and then plus t squared over 2 lambda. Okay? Does everybody see where the 1 went? Why there is not a 1 there anymore? Okay. All right, now we combine the exponentials by adding in the exponent, and what do we get? Well, here's a minus t root lambda. Here's a plus t root lambda. So this and this cancel. If I multiply lambda times this, what do I get? T squared over 2. So what does this say? That as lambda goes to infinity, the moment generating function for Poisson with parameter lambda minus lambda over root lambda converges to the moment generating function for a normal. And by the continuity theorem, and this holds for all x, because the distribution function for the normal is continuous everywhere. Okay. So here's a quick example. If x is Poisson with parameter 81, I don't know. I'm going to have to subtract lambda, 81, so I don't know. 72. Let's just say 72. Okay. Well, actually, we could compute this explicitly. would be that. So we just compute these 73 numbers and then add them together, and we get the answer. And you wouldn't finish this by the end of the summer session, I don't think. Or we could use a normal approximation, in which case we can finish by the break. So how should we convert this so that we can use the normal approximation? Well, we should subtract lambda and divide by square root of lambda. So we should subtract 81 and divide by square root of 81, which is 9. And we get this. And now you should be really impressed, because I made up these numbers at the board, and I came up with -1 here. Okay. So this is about like the probability of normal is less than or equal to -1. And does the table have entries like this?
No.
No. It has probabilities that you're less than or equal to a positive number, so you have to convert this to a probability of that form. Now, if it's normal, so this is approximately the same as the probability that a normal is less than or equal to -1. From now on, if you see z, it's going to be a random variable with which is normal with mean 0 and variance 1. So you have to convert this to something. Let's do it in 2 steps. Is this step correct, and why is it correct, if it is? Yeah, because the distribution for z is symmetric with respect to the origin. The area under the density for z to the left of -1 is equal to the area under the density z for z to the right of 1. The density is an even function. And now how can we convert this to an expression that involves the probability of z being less than or equal to something? Yeah. And didn't I tell you a long time ago that you'd use this thing many times, even though it's very simple? Okay. And now we can look this up. And I'll do that for you. Just look in left column under 1, and then go to 0. It's 0.8413. And that's what .1578. Okay. So this is a pretty good approximation. This is a horrible thing to have to compute. I mean, you could program to get it done, but it's much easier. Okay, now we take a break.
So these are approximations to true answers.
Yeah.
Is there a way of finding
How close?
a margin of error
Yeah.
without actually computing?
Yeah, I'm not sure the book has it, but there's a theorem called the two E's. Yeah, that gives a estimate for the error.
That's independent of the distribution?
Oh no, if the distribution is already close to normal, then the error won't be so. Yeah, so for things like binomial, it's quite good if the random variable has density that's non-zero out at infinity, then it becomes less good. Yeah. So the estimate, I mean, you can get better estimates for some random variables than for others. Okay. Let's do one more approximation. We just covered the normal approximation to the Poisson. We almost did this, but I think it's worth mentioning explicitly. What's the variance of x? Yeah. If p is fixed, and x is binomial with parameter n and p, then this suitably centered and scaled random variable has an asymptotically normal distribution. Now we essentially did this when we were studying sums of Bernoullis. Sums of Bernoullis are binomial. Did we prove that? I don't think we did. How would you prove that? Suppose I asked you on the final to show the sums of Bernoulli.
Show the moment generating.
Yeah, compute moment generating functions. You can do that by computing moment generating function. Compute the moment generating function for this, and then take n independent Bernoullis, add them up, call that Sn, compute the moment generating function for that, and show they're equal, then the two have the same distribution. Do you think you can do that? I'll give you till Wednesday. Wait, today's Wednesday. I'll give you till Friday. If you can't do it by Friday, I'll do it for you. I'll show you how to do it. Okay. Let's see. Let me think about whether I want to use 100. Okay, so 600 would be 36. Let's roll with the die 3,600 times. And let's compute the probability that you have between 550 and 650 sixes. How many sixes would you expect in this many rolls? 600. So we want to know something like that. And I'm probably driving you crazy, but let's leave this digit open for a minute. Because I want to find nice numbers. So of course, you could compute this explicitly. This probability, the probability that if x is the number of 6's, what kind of random variable is that? Well, if you count a 6 as a success and not a 6 as a failure, then x would be the number of successes in 3,600 trials where the probability of success is 1/6. So it's a binomial random variable with parameters 3,600 and 1/6. And we want to know what's this equal to? Well, we could write down the probability explicitly. And this looked horrible, right? You have about 100 terms there if this is 550 to 650. And then you have all these terrible numbers. And you have to compute them and add them up. A computer could do it pretty quickly, but then you'd have to program a computer. Or you could use normal approximation. What would n times p equal here? And what about square root of np 1 minus p? Let's see. np is 600. This is what? 5/6? 600 times 5/6. That would be square root of 500. Is that right? So we have 550 minus 600 over square root of 500. I'm subtracting np from everything and dividing by square root of np 1 minus p, just as in that expression over there. Okay. Well, actually, so this is not approximately equal to. It's exactly equal to. All I did was some legitimate manipulations, but this would be approximately equal than the probability that a normal random variable is between these two numbers. Okay. So what should we take for the middle digit? Maybe 5 wasn't a bad choice after all. Do you think, or is there a better choice? Let's take 5, I guess. Okay. So on the left, we'd get minus 50 over the square root of 500. And on the right, we'd get 50 over the square root of 500. And z is a normal random variable with mean 0 and variance 1. So this looks like, on the left-hand side, probability that, does this become minus square root 5 less than or equal to z less than or equal to square root 5? Square root of 500 is square root 5 times 10, right? So we get 5 over square root 5. That's square root 5. Same thing here. Square root of 500 is 10 times square root of 5. So we get 5 over square root of 5, or square root of 5. Okay, and square root of 5 is what, approximately? Anybody be able to calculate that? Nobody has a calculator? In the meantime,
2.24.
okay. Thank you. Okay, now this we can look up. This one, no, because only things of this form are in the table. So we have to convert this into some expression that has probably z less than or equal to something. So the first thing we do is we make it probably z is bigger or equal to plus 2.24 by the symmetry of the distribution. Okay, and then we convert that into that. Okay, again using probability A as 1 minus probability of A complement. And this becomes twice the probability Z is less than or equal to 2.24 minus 1. And so we can look that up. And I look at 2.2 and go over under 0.04 and get 0.9875. So it's 0.9750. Okay. All right. All right, so I want to go back for a moment to the step from here to here. Here I claim I'm using probability of A is equal to 1 minus probability of A complement, where A is the event Z bigger than or equal to 2.24. So this should be the probability that Z, what would A complement be then? Z less than 2.24. Well, I wrote less than or equal to. Doesn't matter whether I use strict inequality here or not. Why not?
Because the probability that it's going to equal that value is 0.
Okay, you're right. Why?
Yeah.
Right, it's a continuous random variable. For continuous random variables, the probability of it being equal to a specific value is 0. And one way to see that, probably that u is equal to little u, would be less than or equal to the probability that u minus epsilon is less than capital U is less than or equal to u plus epsilon. And this would be f of the distribution function at little u plus epsilon minus the distribution function at little u minus epsilon. And what happens to this as epsilon goes to 0? This goes to f sub capital U of little u minus f sub capital U of little u. Why? The distribution function is continuous. And this difference is 0, and this is bigger than or equal to 0. And this holds for every epsilon. So we conclude that probably capital U is equal to u is 0. Okay? Okay, take a couple examples. Suppose V is Bernoulli random variables. What values could V have? 1 and 0. So what do you think the answer is then? What's probably U is 0? 0. What's probably U is 1? What's the probability U is any fixed value? 0. What's probably U is equal to 0? 0. What's probably U is equal to 1? 0. So what's probably U is equal to V if V is Bernoulli? 0. What if V is binomial with parameter n and I don't care what P is? What values could V have? 0 through n. What's the probability that U is 0? 0. What's probably U is 1? What's the probability U is equal to anything that V could be equal to? 0. So what's probably U is equal to V? 0. What if V is a discrete random variable? This would be 0 because if V is discrete, what's the joint density of these two guys? Well, let me say I can write this this way, right? What have I done here? This event, capital U equal capital V, is the union of these events. These events for different little v are disjoint because capital V can't be two different little v's at the same time. So the probability of the union of these events is the sum of the probabilities. Each one of these can be written what? U and V are independent, right? So I'm going to take two steps here. First step, what does this say that the value of capital V is? It's little v. So what's this? Okay, and now these are independent. And what's this term here? 0. Or back up here, this probability is less than or equal to the probability that u is equal to v, because that would be less restrictive. So what's this probability already? We already know it's 0. Okay? So this is 0. Now let's suppose v is continuous. But actually here, well anyway, if v is continuous, with density f sub v, let f sub u denote the density of u. Then the probability that u and v fall in some set A, where A is a subset of R2, is the integral over A of their joint density. Now they're independent. So their joint density is a product of their individual densities. Okay, that's what densities do for you. So can we express u equal v as an event of the form the pair uv is in a set A? What would that be? A line. It's the line u equal to v. It's this line. Right? So this is the probability that the pair uv is on the line L. And by this formula, it's the integral over L f sub u of little u, f sub v of little v, du dv. Now what's the interpretation of this? This would be the area under the graph of the function, this times this, over the line L. What's that area? What's the area of anything over a line in 2 dimensions? 0. It's 0. This integral is 0. So the probability u is equal to v is 0 if u and v are continuous random variables. This doesn't require independence, actually. Just if I had a joint density here, the same argument would work. So for example, if u and v are independent, continuous random variables, with the same distribution and identically distributed. I guess I could have said IID. What's the probability that u is less than or equal to v? Well, is this true? Well, Is that true? Why would that be true? What's the difference between U and V, statistically speaking? Nothing. They're the same, right? So these two should be the same because U and V have the same distribution. I could relabel them. So we get that. What about the probability that U is less than or equal to V plus the probability that U is bigger than V? What's that equal to? 1. What about the probability that U is less than or equal to V plus the probability that U is, U is bigger than or equal to V? What's that equal to? Why is it 1? Yeah, what's the difference between this one and this one? This one has U equal V. What's the probability U is equal to V? So I've added in here an event of probability 0. So these two probabilities are the same. So this is still 1. Okay. So these two numbers add up to 1. These two numbers are equal. So they must be equal to half. Okay. What's this probability? Well, how do you tell whether roots of a polynomial are real? Use the quadratic formula, right? And see if the so-called discriminant is bigger or equal to 0. What would the discriminant here be? It's u squared minus 4 times this times this. Is it discriminant or discriminant? Thank you. The discriminant is u squared minus v squared. So this would be the probability that u squared is bigger or equal to v squared. And what's that probability?
One half squared.
1/2 squared? No. Here's a random variable, it's continuous. Here's a random variable, it's continuous. They have the same distribution. What's the probability one is bigger than the other? 1/2. Okay. So I think somebody said that the TA told you the answer here was, one of the TAs told the answer was 1/4. It's 1/2. So if you had 1/2 on the exam and got it marked wrong, bring it back. Okay. Okay. Well, so if let's use this. This leads into chapter 6. Let's suppose u is normal with mean 0 and variance 1. Let's look at the distribution of u squared. This was all planned as a segue from chapter 5 to chapter 6. We're now in chapter 6. Distributions derived from the normal. So we'll take a normal random variable with mean 0 and variance 1 and square it. That happens often enough that it has a name. This is called chi-squared with 1 degree of freedom. So let me write that down over here. This comes up in sampling and estimations of variance. If U is a normal random variable with mean 0 and variance 1, then U squared is called chi-squared, and I'll put a 1 here. Sometimes a 1 isn't there, and then it's understood as there, and this is called chi-squared with 1 degree of freedom. And actually, this is going by an alias. It's actually a distribution you already know. And how do we reveal distributions of random variables? We compute the moment generating function and see if we recognize it. And fortunately, it's rather quick to decide because we only know a few moment generating functions at this stage. So let's compute the moment generating function for U squared. So here's our function e to the t u squared. I'm using the density of u. So this is a function of normal random variables. So I evaluate that function at little u, and then multiply by the density. Okay, the density is 1 over root 2 pi times that, and this is the function whose expectation we're evaluating. Now, when you're doing expectations, you should check, don't always, I guess, that the integral is going to be finite, or the sum, or whatever. Is this always going to be finite, this integral? What do you think? What if t is 1? Is this integral finite if t is 1? What are you integrating if t is 1 here? What is this product when t is 1? E to the u squared over 2. And you're integrating from minus infinity to infinity. What does e to the u squared over 2 do when u goes to plus or minus infinity? Goes to infinity. So do you think it has a finite integral? No. So if t is 1, this is not going to work, or it's going to be infinite. For what values of t would it be finite? Well, actually, if t is negative, it's fine, right? But can we get bigger than 0? That's the big question. Can you get t bigger than 0? Because to make these conclusions about uniqueness of the distribution that gives the moment generating function, you need the moment generating function to be defined in a neighborhood of 0. It has to be defined in some interval containing 0. Can we take any positive values of t and have that be finite?
Yeah, any greater than 0.
Yeah, so up to a fourth, for example. Then the exponent is still negative. If t is a fourth, you e to the minus u squared over 4 there, right? And that would be fine. Okay? So this is going to converge in a neighborhood containing the origin. But not for t bigger than or equal to a half. So we're in business. And how would you compute this? Well, I guess first step would be to combine the exponentials. I think I did that right. And how do you do this integral? Well, what does it look like? Have you seen integrals that vaguely resemble this? Well, what kind of density does it look like for what kind of random variable? Looks like a normal. What does a normal density look like? A general normal density is like this. This is the density for normal with mean zero, mean mu, and variance sigma squared. Does that look like this? Not exactly, but not too far. Have I changed anything? Well, I cosmetically changed something, but is this different? Is this unequal?
No.
This is not unequal to what I started with, right? Now does it look like that? Yeah, with sigma to the minus 2 equal to 1 minus 2t, and mu equal to 0. So you have u squared. How would you get u squared here? You'd have to have this be 0. But now, if sigma to the minus 2 is 1 minus 2t, we're missing something. We're missing this. So I should put that down here. If sigma to the minus 2 is this, then sigma squared would be this to the minus 1. So I put that down here, but that's not where I started with. I have to correct by putting in that term. Okay. Now what's the integral of this from 0 to minus infinity to infinity? It's 1, right? So 1 over this times that integral would be 1, leaving that part. Okay. 1 over 1 minus 2t to the half. That's the moment generating function. Do you remember what the gamma moment generating function was? Well, if you don't, it doesn't, it's okay. And this integral converges as long as t is less than lambda, and then you'll get something negative in the exponent at infinity. So we're good here. Let's combine the exponentials. Okay. Now that lambda to the alpha or gamma of alpha times x to the alpha minus 1 times e minus lambda x is a density means that when I integrate this stuff, I get 1 over that stuff. Now I have to integrate that stuff. So I know that it'll be equal to gamma of alpha over lambda minus t to the alpha. Just from the fact of the form of the gamma density. I'm integrating a gamma density here with parameter lambda minus t and alpha. And the correct normalizing constant would be 1 over this. The gamma of alphas cancel, and so the moment generating function for this is lambda over lambda minus t to the alpha. Okay. Does this look like that at all? Well, we have the minus t in the denominator. That's a good sign. What would lambda have to be? 1. Lambda has to be 1. And what would alpha have to be? 1/2. Right? So this is oh wait, is lambda equal? Maybe not. Maybe lambda is not 1. Let's try over there. What's the coefficient of t? -1. Here it's 2. Let's get rid of that. Let's factor that out. Okay. If I factor that out of here, I get square root of 2, right? Is that correct? And if I put this up in the numerator, it becomes 1/2 to the 1/2 over 1/2 minus t to the 1/2. Okay, now lambda is 1/2 and alpha is also 1/2. So this chi squared with 1 degree of freedom is equal to a gamma with parameters 1/2. Okay. Now quickly, if u1 through un are IID normal, mean 0 and variance 1, then u1 squared plus u2 squared plus un squared is called chi squared with n degrees of freedom. And that has another name. What would the moment generating function for that be? Well, in a step that we've done many times before, because of independence and identical distribution, we get this, right? And we just computed this. Here it is. And that's a gamma with what parameters? N over 2 is the alpha, and lambda is 1/2. Okay. So we know the densities for these already. Okay, so we'll stop there and continue on chapter 6 Friday.